In this module, the purpose is to provide new meteorology students with the big picture view of the Earth's atmosphere, including the qualitative relationship between pressure, density, and altitude, and the basics of its chemical composition. In certain ways, the Earth's atmosphere is very much like its ocean. It consists of a fixed mass of fluid bound to the Earth's surface by gravity. Horizontal differences in pressure lead to motions, that is, winds or ocean currents, that redistribute mass. In the absence of external influences, pressure differences would eventually equalize and all fluid motions would come to an end. The atmosphere or ocean would then become a stagnant fluid where nothing at all happens. There would be no weather, no ocean currents, nothing. It's the energy arriving from the sun and the compensating loss of energy back to space via infrared radiation that sustain the pressure differences that in turn sustain circulations. But there's a crucial distinction between an atmosphere and an ocean. In an ocean, the fluid is an incompressible liquid, seawater in this case. In an atmosphere, the fluid is a highly compressible gas, air. An ocean, being incompressible, has a well-defined upper boundary, and the density below that boundary is fairly constant. The atmosphere, being compressible, has no definite upper boundary. To understand that, here are a few key facts about pressure. With a very good approximation, pressure at a particular level in the atmosphere or ocean is equal to the weight per unit area of the atmosphere or ocean above that level. Most of the time. There's exceptions, we won't be talking about those for a while. This is known as hydrostatic balance. The density of air is determined above all by variations in pressure. That follows from what we'll be calling the ideal gas law. Temperature also matters, but that doesn't vary as drastically as pressure. Putting these ideas together, as you ascend through the atmosphere, ambient pressure decreases at a rate proportional to density. But the density is also proportional to pressure, so the density decreases, and the rate at which pressure decreases as well. Graphically, things can be looked at like this. Imagine a system in which we have both an ocean and an atmosphere, and the axis on this plot starts at the bottom of the ocean. And the dashed line is where we have sea level. So everything below the sea level is water, everything above sea level is atmosphere. Now, the density of water, to a pretty good approximation, is a constant, regardless of depth. And so that's indicated by that vertical line at one point on the x-axis for density. It goes to zero abruptly at sea level, and from there, the atmosphere takes over. The atmosphere has a lower density, and that density changes and decreases with height. If we start near the bottom of the ocean, where the pressure is high, and rise up through the ocean, then the pressure will decrease rapidly because of the high density of the ocean, and it will decrease at a linear rate because the density is constant. Once we reach the surface of the ocean, then the density of the air is much lower, and so the pressure change with height is much lower as well. And also, because the density decreases with height, the rate of change of pressure also decreases with height. Since we'll be talking about pressure quite a bit, starting early on, we might as well go ahead and introduce the units of pressure that we use in meteorology. The standard SI unit for pressure is the Pascal, which is defined as a Newton of force per meter squared of area. Traditional meteorological units are millibars. 1 millibar equals 100 pascals, which is the same as a hectopascal. The abbreviation for hectopascal is HPA. Hectopascals and millibars are the same unit, just with a different name, but the hectopascal name reminds you that it's really 100 of the SI units, which are pascals. If you're talking about pressure to a meteorologist, especially an older meteorologist, you may find that millibars are what are commonly used to describe where you are in the atmosphere. Just remember that that's the same as a hectopascal. To confuse matters a little, there's a number of other units that are also very common in meteorology. First of all, we can talk about standard pressure at sea level as being 1 atmosphere. which is defined as 1013.25 hectopascals. So if we talk about pressure in units of atmospheres, we're talking about multiples of that standard pressure. Since a hectopascal is 100 pascals, and a millibar is 1/1000th of a bar, 1013.25 hectopascals is about 1.013 bars. And a bar is therefore just about the same as an atmosphere. Because of the reliance in the old days on mercury barometers, standard atmospheric pressure is often expressed as 29.92 inches of mercury, which is the same, by the way, as 760 millimeters of mercury. The latter unit of millimeters of mercury is most often used in laboratories by chemists. Knowing these equivalences makes it very easy to compute between one unit and the other, because if you know that 1013 hectopascals is the same as 29.92 inches of mercury, then if you need to convert 28 inches of mercury to hectopascals, you simply divide the 28 by the standard amount 29.92 and then multiply by the standard amount 1013.25 and get 948 hectopascals. So it's an easy conversion that has helped a lot if you simply remember these different values for standard pressure. Let's talk a little bit about density. The conventional symbol for density is the Greek letter rho, sometimes with a subscript to indicate which density we mean. So I may use rho d to mean the density of dry air. I may use rho w to mean the density of water. If I leave the subscript off and just call it rho, it depends on the context, but I'm often just talking about air in general. The unit of density in the SI system is a kilogram per meter cubed. Kilograms, 1 kilogram is 2.2 pounds in the English system, and a meter cubed, if you're not able to visualize exactly how much that is, it looks like that collection of boxes right there. That's about a meter by a meter by meter. So the density of air near sea level is about 1.2 kilograms per meter cubed. It depends a little bit on temperature. It depends even more on pressure, but that's a nice round figure for the density of air at sea level. Water, on the other hand, has a density of 1,000 kilograms per meter cubed, which is 1 metric ton per cubic meter. That makes water about 800 times as dense as air near sea level. A convenient fact that makes it easy to remember the relationship is that 1 liter of pure water has a mass of 1 kilogram, and there's 1,000 liters in a cubic meter. Given what we know now, we can look at how we might go about calculating the entire mass of the atmosphere on Earth. As we already stated, we can view the pressure at any given level as the weight of the atmosphere per unit horizontal area above that level. Weight, that is a force in newtons, is given by mass, usually expressed in kilograms, times the acceleration due to gravity, g. Pressure is weight per unit area, which is the same as newtons per meter squared, and it can be thought of as a mass per unit area times g. Therefore, if we ignore variations in g, and that's usually not too bad of an approximation, we can calculate a pretty good estimate of the total mass of the Earth atmosphere as follows. Take pressure at sea level and divide that by g. That turns the weight per unit area into a mass per unit area. Then multiply that mass per unit area times the surface area of the Earth in square meters, and that will give the total mass in kilograms. If we ascend to a level where the pressure is 1/2 that at sea level, then we have left half of the atmosphere below us in terms of mass, with the remaining half above us. This typically happens near 5.5 kilometers, or about 18,000 feet above sea level. Let's talk now about atmospheric composition. With the exception of water vapor, ozone, and a few trace constituents, the atmosphere below 100 kilometers is well mixed. This means that the proportions of other major constituents are nearly the same everywhere. Water vapor and ozone are not well mixed because the rates at which they are added to and removed from the atmosphere at any location are faster than the rate at which the global atmosphere mixes. Water vapor is added by evaporation and transpiration by plants. Water vapor is removed primarily by precipitation. Both of these processes can occur fairly quickly, over hours or less, and change the amount of water vapor in the air more rapidly than the atmosphere as a whole can mix and make a uniform mixture everywhere. The idea of mixing is similar to when you put a spoonful of sugar into a glass of iced tea. When you first add it, it sits at the bottom and is not well mixed. Once you stir it and dissolve the sugar and blend it thoroughly throughout the glass of iced tea, then the concentration of sugar is about the same everywhere, and it's not likely to change unless you add more sugar or find a way to remove sugar. Now let's look at the specific constituents of the atmosphere, starting with the most prevalent. This table right here shows key constituents ranked by fraction by volume relative to dry air. First, we'll look at the so-called permanent gases, starting with the most prevalent three: nitrogen at 78.1%, oxygen at 20.9%, and argon at 0.93%. Collectively, those three alone add up to 99.93% of dry air. In other words, almost all of dry air consists of those three constituents. Water vapor is a special case. It varies tremendously from one location and time to another. The atmosphere can be very, very dry and have essentially zero water vapor in it at one point in time and space. In a very humid environment, it can be as much as 5% of the entire mixture of gases. Carbon dioxide is another variable gas. It's a trace gas now. It's only present in the amount of about 383 parts per million. But hold on, that was what it was when I wrote the book in 2007. In 2020, it's now about 412 parts per million. It's been increasing at a rate of about 1.7 parts per million per year since I wrote the textbook. Let's take a closer look at carbon dioxide. This is a famous curve of data collected from the peak of Mauna Loa in Hawaii, on the Big Island of Hawaii. The starting point is in 1958, which happens to be the year I was born. And the ending point of this plot is the present, 2020. That's where we are now. And during that time, the concentration of CO2 in the atmosphere increased from 317 parts per million to 412 parts per million. That's a 23% increase in my lifetime. The reason Mauna Loa was picked as a location for monitoring global carbon dioxide is because the mountain peak is quite high, and it's out in the middle of the Pacific Ocean, and so it's not affected by sources of carbon dioxide nearby like cities, continental land masses, and other things. It's representative of the concentration of carbon dioxide in the free atmosphere away from sources. One thing you'll notice right away is that the amount fluctuates, and you can see it zigging up and down as you go up the curve. Every year it shows a complete cycle up and down, and if you look at the average cycle over each year, it looks like this, with increasing carbon dioxide concentration in the spring until we get to about early April, and then it begins to fall rapidly, and it continues to fall until we get to early fall, and then it begins to increase again. What effect do the seasons have on the atmospheric concentration of carbon dioxide? Think about when plants are growing most rapidly. They tend to be growing during the warm season, which is during the late spring and summer. And during that time, we see that photosynthesis is reducing the carbon dioxide concentration rapidly. Once photosynthesis ends for the fall, then the decay of vegetal matter in forests and other locations releases carbon dioxide, and it goes back up again. So we basically have a cycle where carbon dioxide is being drawn down by photosynthesis by plants, algae included in the ocean, and it's increasing again through the cold season as dead plants decay and photosynthesis is not sufficient to keep up. You might be wondering, well, why is there an annual cycle given that summertime in the northern hemisphere is wintertime in the southern hemisphere and vice versa? Well, the reason for that is that there's a lot more landmass in the northern hemisphere, and so photosynthesis by forests and grasslands and so on in the northern hemisphere have a much stronger seasonal cycle than what you would expect from the relatively small portion of the southern hemisphere that has land vegetation on it. And so it's the northern hemisphere cycle that dominates what we're seeing in this curve right here. Why is carbon dioxide increasing overall? It's increasing primarily because of the utilization of fossil fuels. And by fossil fuels, we mean basically any carbon-based material taken out of the ground, including petroleum, coal, and natural gas. And we're now burning the products of these fossil fuels in the form of gasoline in automobiles and as fuel in power plants, even in the manufacture of concrete, which is not as well known a source of greenhouse gases, but one that's very important. Human activities are adding carbon dioxide to the atmosphere and ocean faster than it can be removed by photosynthesis by plants. As a general rule of thumb, we can say that about half of what gets put into the atmosphere remains in the atmosphere. Now, there's really important implications of this change of carbon dioxide. First, there is no doubt that carbon dioxide in the atmosphere is increasing and that it's due to human activity. Second, there is no reasonable doubt that increasing carbon dioxide is warming the global climate, acidifying the oceans, melting polar ice, and already having a profound and measurable effect on land and ocean ecosystems as well as on global weather patterns. Now, this course will not talk about climate or climate change. We have several relevant undergraduate courses that address climate and climate change, including 102, 171, 323, 332, and 425. Back to the constituents of the atmosphere. We talked about the three major permanent gases. We talked about water vapor briefly. We talked about carbon dioxide. Let's look at the less prevalent constituents. These include more permanent gases. These are the noble gases, neon, helium, and krypton. There's not much of these gases, but they are part of the total and shouldn't be forgotten. They're inert. They have no chemical importance. They have no importance for absorbing sunlight. They're just there. They take up space. The remaining gases are so-called variable trace gases that include methane, nitrous oxide, carbon monoxide, ozone, and chlorofluorocarbons as just examples. There's other trace gases as well, but those are the big ones. And by big, they're still small in terms of absolute amount. Methane is only present in the amount of about 1.7 parts per million, but that's increasing, again, due to human activities. It's also a greenhouse gas, so people are monitoring methane. Nitrous oxide is even less. Thankfully, carbon monoxide is less still since it's a poisonous gas, but there's a very tiny amount of it in the atmosphere. Ozone is a big one. We'll come back to that in a second. And at the bottom of the list here is chlorofluorocarbons, which consists of a variety of different compounds that consist of combinations of carbon and chlorine and fluorine. The amount present is very, very small, 10 to the minus 10 as a fraction of the volume of the atmosphere. But there's several interesting and important things about CFCs, or chlorofluorocarbons. First, they are entirely human-made. If you find a molecule of a CFC in the atmosphere, it's guaranteed to have been made in a factory. It simply does not occur in nature. Second, we learned the hard way in the 1990s that CFCs have a destructive effect on the ozone layer, which we'll talk about in a moment as well. And so it was necessary to limit the emissions of CFCs so as to avoid damaging the protective layer of ozone that we depend on to protect us from ultraviolet light. Returning to ozone, let's take a closer look. Its concentration is highly variable. It's high both in the stratosphere, which is the upper portion of the atmosphere above the layer that we live in, pretty much at the altitude where jetliners fly and higher. It's also prevalent in polluted air near the surface in cities. So the value can be as low as 0 parts per million in clean air and as much as 12 or maybe even 15 or more parts per million in other locations. Let's take a closer look. You may have heard that there's good ozone and bad ozone, though both are actually the same chemical compound. Good ozone is ozone that is high in the atmosphere where it absorbs dangerous ultraviolet radiation that would otherwise reach the surface. It also has a profound effect on the temperature structure of the atmosphere, as we'll see in the next module. Bad ozone is down near the surface where we can breathe it and where it can injure plants and degrade organic materials. It's one of several important components of what we call smog. Now, regarding the degrading of organic materials, you probably have at some point removed a rubber band from a desk drawer that was lying there for a year or two, and you thought you could use it, and the moment you stretched it, it immediately snapped. And you found that if you pulled on it just a little bit, it would just fall apart. And you may have found rubber tires that were cracked and brittle and needed to be replaced because they had lost their flexibility. Those are classic examples of what ozone can do to rubber and other organic materials. If you find a rubber band that's not able to stretch anymore, chances are it's ozone in the air that damaged it. Ozone can damage other organic materials as well, including the linings of your lungs and vegetation. And so, from a practical point of view, ozone is a hazard to human health as well as to the health of vegetation. Let's take a closer look at the so-called ozone layer, which is what we consider to be good ozone. It's a region of the upper atmosphere between around 20 and 60 kilometers or so of altitude that's characterized by the presence of ozone created by ultraviolet radiation acting on oxygen. The highest fractions of around 10 to 15 parts per million are usually found around 30 to 40 kilometers altitude. That can vary, but that's fairly typical. Ozone is found above and below that range as well, but that's typically where you find the most ozone. An important point to make here is that we're still talking about only 10 to 15 parts per million. So you don't find a layer of pure ozone or even a high concentration of ozone at those altitudes. All you find is air that is enriched with a small amount of ozone to the tune of about 10 to 15 parts per million maximum. The reaction that leads to that is actually fairly simple. We have a regular oxygen molecule, or O2, which is encountered by a photon of sunlight, and we're specifically talking about sunlight with wavelengths which are shorter than 0.24 micrometers, and that's a photon that has enough energy to split the O2 into two oxygen atoms. Those oxygen atoms don't like to be alone, so they will run into another oxygen molecule and immediately combine again to form ozone. And so we get an O3 on the right-hand side of this equation. Now let's look at smog, or bad ozone. Actually, bad ozone is part of smog. There's other constituents as well. Low-level urban air accumulates pollutants from automobiles and industrial sources, and even some natural sources. I'll mention those in a second. The first we'll mention are volatile organic compounds, or VOCs. VOCs are any organic materials that easily evaporate into the air. This could include gasoline, solvents, paint thinner, what have you. And not all VOCs are human-made. Some plants and trees and so on give off VOCs as well. And if all we had were VOCs in the atmosphere, that would not necessarily be a terrible thing as long as it's not too much. But once you throw into the mix nitrogen oxides, commonly known as NOx, NOx, then combining those with sunlight can lead to fairly complicated chemical reactions that create ozone and other nasty components of smog. Ozone levels are typically expressed in parts per billion by volume. We already expressed them in parts per million for the ozone layer. We'll see that comparison in a second here. If you look at the clean background values of ozone in the atmosphere prior to industrialization, we believe that the natural background was around 10 to 20 parts per billion of ozone. Nowadays, if you look at remote locations in the northern hemisphere, such as Greenland, northern Canada, the northern oceans, and so on, you may find values of 20 to 40 parts per billion, depending on season and latitude. Rural areas can occasionally see values of ozone concentration up to 80 to 100 parts per billion just based on spreading from urban areas. And urban areas themselves commonly see 120 to 200 parts per billion during pollution events, with maximum values being measured in really polluted cities like Los Angeles and Mexico City of around 490 parts per billion. We're way, way, way up from the background prior to industrialization. Now, we just talked about the ozone layer, and up there we can find values as high as 15,000 parts per billion. That's 15 parts per million, as I mentioned before. But in parts per billion, it's 15,000. And just for reference, the health standards for ozone, for breathing ozone, basically limits exposure to 125 parts per billion if you're exposed for an hour or less, 85 parts per billion if you are exposed to ozone for more than 8 hours. So that puts these numbers above in perspective. Urban areas frequently exceed that. The worst cases are far worse than that, and clearly you don't want to spend any time living in the ozone layer. Finally, let's take a quick look at what things look like in the far upper atmosphere. It's not a place that you're likely to be concerned with very often, but as new meteorology majors, you probably should at least have an idea of what things look like even far from home. Below about 100 kilometers, as I mentioned, the atmosphere is well mixed. The atmosphere behaves like a fluid, and the proportions of permanent gases are essentially constant everywhere. Again, think of the analogy of the glass of iced tea with the sugar stirred into it. If it's well mixed, the concentration of sugar is everywhere throughout that glass. As long as mixing is rapid enough to overcome anything that might separate the constituents of the air, you're going to find the same proportions everywhere. At higher altitudes, above 100 kilometers, collisions between molecules become much rarer. The atmosphere no longer behaves like a fluid. You don't have just a collection of molecules all kind of moving together and colliding with each other all the time to form what we typically think of as a gas. Instead, individual molecules follow long parabolic trajectories like bullets. It's basically like if you shot a rocket up into the air at a high rate of speed and it follows a long arc and then eventually comes back down again. Lighter molecules have higher speed and travel farther vertically. And what that means is that you will tend to find the lighter molecules at higher altitudes and heavier molecules at lower altitudes. Again, all above 100 kilometers, but you start to see separation by molecular mass. The other thing which is going on at these very high altitudes is that because of the very energetic solar radiation that is reaching these molecules at very high altitudes, many of the molecules are broken into the constituent atoms by the radiation. If we look at a graphical depiction of the composition of the atmosphere by altitude, going all the way up to 1,000 kilometers, which is basically getting far out into space. First, let's look at the horizontal axis. We're looking at fraction by volume, and we're looking at it in percent, and it's a logarithmic axis again. So we're going from 100% to 10% to 1%. We're going by factors of 10 for every label here. So helium, which is present in a very low percentage of much less than 0.001%, is shown here as a dashed line. And up to 100 kilometers, it's a constant proportion. Argon is present in an amount close to 1%. So we see that dashed line at about 1%. Oxygen is 21%. Nitrogen is 78%. So below 100 kilometers, the proportions are well mixed and constant throughout the depth of the atmosphere. You'll notice the dividing line right at about 100 kilometers where everything changes. It changes a little bit below, but the transition occurs over a few kilometers above and below 100 kilometers. The first thing you'll notice, let's take nitrogen. Nitrogen is steady in concentration, 78% up to about 100 kilometers, and above that it begins to fall off rapidly for a couple of reasons. One is that it's a heavier molecule, and so it tends to be displaced by lighter molecules like hydrogen and helium. The second is that it breaks down in the sunlight into just N, so you have nitrogen atoms instead of N2 as a molecule. And you'll notice that the N concentration starts at basically 0 and rapidly increases. And by the time we get to about here, we're seeing equal concentrations of N2 and N. Likewise, oxygen hits that crossover point at a slightly lower altitude. And we also have hydrogen, which is present in extremely small quantities, but comes from water vapor. By the time we get to very high up here, we're seeing higher concentrations of helium and hydrogen and some atomic nitrogen, oxygen, but no O2 and no N2 in any significant amount anymore. The area where it's well mixed, the layer within which it's well mixed below 100 kilometers, is also known as the homosphere. You can think of homogenized milk, where everything in the milk is all blended together equally, the cream and the milk. Here, the atmosphere is blended together thoroughly, and that's why it's called the homosphere. And above that, it becomes the heterosphere because gravitational separation as well as dissociation of molecules means that it's no longer an equal mixture everywhere. We get varying proportions of the various constituents depending on molecular mass and so on. Just as an aside, that 100-kilometer level is the conventional beginning of what we call space. Typically, when we talk about where space begins, people usually think of 100 kilometers as being roughly that altitude. The reality, of course, is that space does not become a sudden vacuum right away. We still have these gases at higher levels, but they no longer really behave much like a gas, and their concentration falls off pretty rapidly, so it doesn't take long before you're essentially in a vacuum. Okay, that pretty much concludes this first module. What we covered was the basic physical properties of the Earth's atmosphere, including mass, density, pressure, and hydrostatic balance. Now, we talked about these things qualitatively or descriptively. We will talk about some of these things mathematically fairly soon. We talked about the basic chemical composition of the atmosphere, emphasizing the so-called permanent gases which make up dry air, and then briefly discussing water vapor, carbon dioxide, ozone, and other trace gases as so-called variable gases. Now, the last three of these I mentioned primarily just because you should have a basic understanding of the presence of these gases and their potential role in specific problems relating to the atmosphere. For this class, the dry air portion and the water vapor are going to be the components of the atmosphere that we care about exclusively going forward.